Welcome back. In this lecture, we will introduce this important topic, reaction cross-section in nuclear fission. But we will revisit this topic many times later in the series of lecture, especially in the context of U-235. But we'll just get started with some general features. In general, the fission reaction cross-section indicated by sigma F is greater for nuclides with odd number of neutrons. You may anticipate why this may be so, because there is something called pairing energy. So when you irradiate a nuclide with odd number, uh, there is a pairing energy which is advantageous. So in general, you would anticipate sigma F to be greater. Sigma F for light elements is less. It is so less, it is typically not measurable with thermal neutrons. By thermal neutrons, we refer to neutrons which have an energy of 26 milli electron volts. So that is what is the energy at room temperature. So typically, this is very low for light elements. For elements that have atomic number greater than 85, the fission cross-section is also possible. It's measurable when they are bombarded with rather high energy alpha particle or protons. Uh, why do we need high energies? Because there's a Coulomb repulsion. So when alpha particle or proton approach the nucleus, they are decelerated. Therefore, unless they have sufficiently high kinetic energy, they cannot really impact the nucleus. So you need rather high energies for fission if you use alpha or protons for fission. As opposed to this, just contrast this scenario, because neutrons are neutrally charged. There is no Coulomb barrier. That's why neutrons are very interesting for nuclear reactions. For actinides, we will clarify what we mean by actinides. Even thermal neutrons are good enough to cause fission. So the reaction cross-section is significant to cause fission. So what do we mean by actinides? These series of elements are what are referred to as actinides. Both actinides and lanthanides, which is this series, are based on the first element. These are called lanthanides because lanthanum is the first element in this series. These are called actinides because actinium is the first element. Okay, so these are called rare earths for nuclear science and engineering. These are what are very interesting. And the most interesting is, of course, uranium. Plutonium is also important. There are other important elements, especially for India, thorium, and so on. So if you look at the nuclear cross-section, on the y-axis, we are plotting sigma F. As you know, the units are in barns. Note, this is for U-238. Okay, so this is the less interesting isotope of uranium, but this is the most abundant isotope of uranium. So to have cross-section, the general behavior is that the reaction cross-section increases with increase in neutron energy. And we are really talking about rather high neutron energy. We are not, the thermal neutrons are somewhere way below here. So as you increase the kinetic energy of the neutrons, the fission cross-section will increase. Here, the data is from rather small energies to about 37. There is a stepwise increase. We won't go into the reason why there is a stepwise increase, but this is the general behavior. Contrast this behavior with a cross-section which we have discussed when we introduced this topic of reaction cross-section. We had shown this plot. This is the reaction cross-section of silver. So there is a general 1 by V behavior, right? As the kinetic energy increases, the cross section decreases. That's what we mean by 1 by V. As V increases, the reaction cross section increases. But at certain specific energies, there's a sudden increase in cross section. That is because of resonances. So we had already discussed this plot in an earlier lecture. In the next lecture, we will go into greater detail. We will look at some of the mechanism and the reason for nuclear fission to have an activation barrier. That's going to be the topic for the next lecture. Thank you.